Hello once again. So, in the last video, I've just explained you some of the assembly instruction usage in the ATMEGA microcontroller. So, let's look into some of these, some more arithmetic instructions apart from the addition. So, here in this addition, if you just look at this example here, there is an example assuming that a RAM location 400H. So that's the data RAM. It's having a value 33H. Now write a program to find the sum of the location 400H of the RAM and 55H. That's the value, literal value. At the end of the program, R21 should contain the result. So what the question statement is actually? So we should have, there is a location which is 400H, and in that location I'm going to have 33. And there is another value which is loaded in the register 55 to the register 50, some literal value. I should add this to content and I should store this result in R21. That's the problem statement. And if you see here, so we assume that the 400 will be having this value. So there is an LDS instruction which takes the content of this 400 to R2. So what does R2 now? After the execution here, R2 will have 33, correct? So then LDI 21, so R21 will have 55. So there is an add instruction which is executed. So it's straightforward. So 33 plus 55, it is going to be 88H, no doubt. So how do you find the status of the flags and all? So you need to actually work out this in the bitwise. So just look at this. I'm going to write 0 0 1 1 0 0 1 1, that is 33, 0 1 0 1, then 0 1 0 1, that is 55. If you add this content one by one, 1 plus 1 is 1 0, then 1 0 1 0 1. This is again same. So 0 0 0 1, correct? So if you look at this, 0 flag is 0, carry flag is 0. What about auxiliary carry? Is there is any carry over from this position? No. So H also 0. And that's how you decide. Okay. So this is how this program is written. Now let's look into add with carry, that is ADC. Okay, so ADC is useful whenever we are going to add a 16-bit number. So depending on what is the basic addition available, if your number is increasing, then obviously this is how. So you remember when you are adding say number, let's say 1 2 3 4 and 5 6 7 8. So if I want to add this, the usual rule is we'll add these two first, then if there is any carryover, we'll take it here. That's a regular addition. So it's the same technique. So what is the difference is, I will be using this as a usual add instruction. Okay, and obviously this has to be done depending on what is that carry that I'm going to get it from this. So this set of numbers should be added with the another thing called add with carry, because obviously I should consider this, any carry out is there from this point. So that's why add with carry is there. So if you look at these examples here, they are given addition of two 16-bit numbers. The numbers are is mentioned over here, 3C and 3B8D. Okay, 3CE7, 3B8D. They are the two numbers, and these numbers are stored in this location. That's already defined. What I need to do is I need to replace these registers such that you look at this. So add R3 comma R1. So I supposed to add this and this first. So E7 is in this right here, R3 is there, this is the first one, and then R1 is here, 8D. Can you see here, 8D E7. So I am adding R1 and R3. Whatever result come, that will be saved in R3 now. Along with that, the carry flag will set or reset depending on the outcome of this instruction. That has to be added with R2 and R4. That's what I'm doing. R4 comma R2 I'm adding with carry. That's how this is add with carry is done. So we can move on next, subtraction. So subtraction is what we am discussing is about the unsigned numbers, okay, not for the signed numbers. So there are two subtractions instructions are there here, sub and subb, like you have it for add with carry and simply add. Now if you look at this in AVR, there are 5 subcategories are there. So this is the basic format of the sub instructions. It's very clear to look at the sub rd comma rr, where this rd is equal to rd minus rr. So straightforward. This is sbc. What do you we have sbc means it is subtracting the carry, which you say borrow, okay. And you have subi, which is a literal value that you are subtracting from rd minus k, and that is with borrow. And there is one more here. So this does rd plus 1, rd equal to rd plus 1, rd minus k. So we'll look into this later, okay, this part of the instruction. Let's look into the first beginning of these 4 categories. So now what it does here is, okay, now how this addition is performed? Addition is performed basically using the the subtraction is performed basically using the addition logic only. They take 2's complement. So any number, 2 numbers to be subtracted, then the one of the number is taken 2's complement. Okay, so how do you take 2's complement? First take the 1's complement, add 1 to it. Okay, then you just add those two, and whatever the result comes, that is the subtraction result, and you have to invert the carry. That's how the basic addition, basic way of implementing this sub logic inside the controller. So with that, let me take up some examples here. Write a program to subtract 18h from 29h and store it in 21. The two methods we are asking, one is without using subi and with using subi. So, the example, if you see, without using, if you see, the two numbers are loaded to the register and simply use sub. That's a straightforward subtraction. There is no doubt. Another thing is using subi. So only one register is taken into consideration, loading 29. Other is literally the value which is taken 18 as it is with the subi. That's the only difference. So just to take a closer look at these instructions one, so that just try to understand how they are implementing. Multiplication is another instruction here. So where we can multiply two numbers by multiplication. What I am doing here, there are again category for unsigned and signed. Okay, so two are there. So simply mul, if you do, it's unsigned numbers, and muls is a signed number, and mulsurd are unsigned number with the signed numbers. Okay, so uh, one can be signed and can be unsigned, so that also can be done. Let's look into that each one of those basic multiplication. Let's have a look how it is done. See, when you are multiplying two numbers here, mul rd comma something, let's see here an example. Always whatever the registers are, the result will be always stored in the R0 and R1. That's what the important thing you need to consider. R0 and R1 will be having the results. So take a closer look at these example. If you want to multiply 25h into 65h, then they are loading those to R23, R24, and you just look at this instructions. It multiplies, assuming that result will come in this. So we can actually execute. We will have a look into the simulation part once, how these instructions are going to show you the results. Now, division of unsigned number. So division logic also we will see. See, now in AVR there is no instruction for divide. We don't have div instruction here. What we have is only SUB. So what they are doing here for the division is successive subtraction. That's what we do here. So for example, if you wanted to divide a number, let's say 8 by 2, if you want to divide, what I'm going to do is, I know that 8 by 2 is 4, and I'm going to achieve this by repeated subtraction. What I'm going to do is, I'm going to do 8 minus 2, I'm going to get 6, then I'll do 6 minus 2, I'm going to get 4, then I'm going to do 4 minus 2, and get 2, then I'll do 2 minus 2, which is 0. Now, how many times you performed till the number becomes 0? So this is the incremented. This is the first time, second time, third time, fourth time. So this 4 indicates the answer. So you do a repeated subtraction and you get the answer. So that's how. So anyway, if your number always the quotient and remainder, this is a quotient, remainder is 0 here. So if you are dividing 9 by 2, then obviously you will be left with 1. So the 1 is going to be the remainder. So same logic is going to be implemented in this program here, when you are actually working on divide instructions. So if we'll have a closer look at this, this is actually the way of defining some of the assembly directives, we say. If you wanted to define something, instead of register putting there in the instruction, if you want to put some uh, terminologies like num or denominator, quotient, you can define it instead of registers. So definition, we say hash define, we use in C. Similar way of declaration here. So it is declared as num is declared as 20, R20 means when the program, wherever you declare num, it will be replaced by the R20. It is actually the property of the assembler. Okay, it's a property of your assembler that takes care of it. But in reality, when it comes to machine language, there is no way you can handle these things. They are literally, these are converted. Only this is what exact register has to come for conversion. So here you see LDI num comma 95. It is nothing but LDI R20 comma. So actually it is nothing but replacing this LDI R20 comma 95. Okay, that's what the meaning is. So I'll be taking this 95 value to num. That means I remember here, here 95 should be the hexadecimal equivalent will be load. Now 95 is in decimal. I supposed to write actually it as 0x. Okay, 0x95 hex value. If you simply write 95, then automatically the hex to decimal to hex conversion happens and the value will be loaded. Here also it is divided by 10. 10 means 0a. Okay, it is dividing it by 0a. So number is 95, this is 10. So if you wanted to do that, then you see how it performs the job. So clear the quotient, that is cleared, that is a register CLR instruction. Some instructions will come here. Now let's look at this. So they are dividing 95 by 10. Okay, that's what the logic here. So you know that this division I'm doing it by successive subtraction. So I'll write it down here, 95 by 10. What I'll do is 95 minus 10, first time you get 85. Okay, so before I go, so this quotient will be incremented by first set of subtraction. When you do first subtraction, before that only you increment it, an advanced increment that I do, and I do perform the subtraction here, and I check. This is actually for checking the carry, a special instruction that I need to loop here. Okay, I'm checking what is this actually, the branch if carry is 0. So if there is a carry flag generation is, if that carry flag comes, then it has to loop back. Okay, it's a repeated subtraction, what I mean. So if there is no carry, if the carry is 0, it will keep on repeating. If carry is 1, it comes out of, that means it is overflowing. So it will perform continuously subtraction until this number. Okay, now what happens, 85 minus 10, then 75 minus 10, so on, it will keep on. Then finally 5 minus 10 comes. Here you get some carry flag. So that time iteration has gone till 10 times, one more extra. So the quotient will have that answer. I performed an extra subtraction. For that, I should decrement this quotient, and also I get back that remainder by adding that extra subtraction is made. That's a very simple technique of addition, subtraction, successive subtraction for implementing the division logic. So this is how the division is to be performed. So probably this you have to keep it in the mind. Now there is one example over here, the application of a division, like when you are performing some number conversion. For example, you have some number in hexadecimal value. I want to convert it to a decimal value. Then how do you perform? So there is a logic for that. So any number you take in a hexadecimal domain can be converted to a decimal. There are different methods. Okay, so we can go for the division method as well. So if you tell me a simple example, for example, I need to divide. Let's say let me take a number called 16. Okay, I wanted to convert it to, this is hexadecimal number. Let me tell you, 16 is the hexadecimal number. I should convert it to decimal. How do you perform? So I supposed to divide this number by 10. Okay, I should divide this number by 10, that is 0x0a. A is actually 10. So you have to perform this division. So once you perform division, you get quotient and a remainder. Obviously this goes one time, and the remainder that you get is actually, this is 16. So if you just perform this particular division, so 16 is, let it go 2 times. I guess it is 2 times, it is not 1 time. So if you perform, let me open a calculator here. So 1 second, I think it is 25. Yes, okay. I'm going to just use a scientific calculator here. Let me, yeah, so okay. So 16. Okay. Okay, it goes 2 times here, and remainder is 0.5. Okay, so you can just cross check this answer. So this answer is supposed to be 25. So 16, if it is the hexadecimal value, then these are two numbers are actually in unpacked, we say. So this answer is supposed to be 25. What do you mean by unpacked? Means the numbers will be the higher digit will be separate, lower digit will be separate. So 0 to 05, this is called as unpacking. So the number will be come in the unpacked format. So any number you can take. For example, I may take it as 0, let's say 0c. And let me take up another example. 0c, if I tell you, now how do I compose? So you know that 0c is actually 12, right? 0c is nothing but 12. So if you divide, then the quotient and remainder, if you see, the quotient will be 1, remainder is going to be 2. So this is actually the answer. 0, 1, 0, 2. If you combine this together, 1, 2, that's the answer. So this is the logic used. You can actually work out this logic even for any number. Just keep dividing it by 0a. Now the problem again here is we don't have a direct division instruction. We should go with successive subtraction. Look at this code once. I'm going to perform this here. So if you look at this code, okay, here is a number that is to be converted, FD. FD is a number we wanted to convert to decimal. So how do they do it? So you look at this here, 10, okay, 10 is loaded. 10 means 0x0a. 0x0a is actually 10. That is loaded to denominator. So this part of the code here is actually doing the division, okay, this part over here, first set of division is performed. So once you get the answer over here, you get the answer for one of the division. Any one division is how many times the division has to be performed. There is again a logic over here. So I'll be keep performing the division. Look at this. There is a decrement, then adding the denominator, so you get the remainder and a quotient. So now I will actually take out the quotient, whatever I get. Okay, I'm going to get the quotient. So here what happens is the if that the remainder that I quotient that I get, the quotient that I'm getting, that number also should be less than 10. Okay, the quotient also should be less than 10. If it is more than 10, I should repeat that whole iteration. So that is performed here. You see, you are actually making now the quotient as a new number. So this will be applicable if the number is greater than 100. 99 is fine. When it goes more than 99, then you need this logic. So whatever the answer we get here, quotient and the remainder, one of the remainder is one of our result, but the quotient here what I get, that will become a new number for the division. That happens in the next set of the division. So this will be the first set of the division. This is going to be the second set of division. So here actually performs first set of division, and here we perform second set of division. I'm going to perform the second set of the division. So I'll get my final answer in this quotient and remainder, along with this remainder what I get here. So that's how this result is going to come. Probably I'm going to simulate this in the lab exercise, okay, this particular division program. So it will be very clear when you are, so same program we will actually execute in the lab. Now there are some pretty simple instructions with the logical and compare instructions. You can just have a look at these logical instructions here. So there are AND, OR, XOR, complement, negate, and compare. Okay, they are something of a logical kind. So all these are bitwise operations. They are all bitwise. So any number you take bitwise, you just perform this addition, AND, OR, XOR, complement, negate, all that. So some special instructions are the compare instruction is something that is important. So obviously compare instruction supposed to be checked with the carry flag. That's obvious thing. So carry flag is what I say, C flag. So this is a carry flag. So carry flag is to be checked. What happens when RD is greater than RR? Then obviously carry is 0. If RD is less than RR, then carry is 1. How do you check 0 of equality? 0 flag. If 0 flag is 1, then RD equal to RR. That's a very simple logic with the compare instructions. So based on this CP, we execute a branch instruction. So usually that's a case. Now if you see, look at this branch instructions. There are a lot of branch instructions related with this. So branch equal, branch not equal, branch if higher or same, lower, lower less than. So lower less than, there's a difference. Okay, look at this signed number. So signed number is different, unsigned numbers you have a different way of logic. Okay, similarly you have greater than or equal, then you have overflow flag also you can check, and you can check overflow flag clear set, both you can check. So here is the instruction branch if not equal instructions for the looping. So how do you do it? Just an example is given. For example, you wanted to iterate. Okay, this is something like your for loop, I say. If you are using a for loop in a C, similar way, I should decrement the register and check whether if the branch if not equal. So if decrement, if Z flag is not set, okay, that's going to be continuously, it's going to iterate as many times possible. So that's how the branch instruction is useful. So here is a simple program. Write a program to monitor port B continuously for 63H. Write a program to monitor port B continuously for 63H. It should stop monitoring only if port B is 23. So very simple. So what is supposed to be done? So you supposed to first you're supposed to make port B as input. So I'm just giving you some insight about this here. So usually in AVR controller, if you want to configure any of the port as input or output, there are two things. So you need to actually make it first. See, you have, let's say, port B, let's say. I wanted to make port B can be made as input or can be made as output. So how do you make it? There is a control register for this port B, which is called as DDRB. Okay, I will discuss more onto this since it is only for registry and some programming skill. So it may be quite difficult, but later when you look back and refer it here, then it will be easy. So what we basically do here is, first I will be configuring this port B as input. For that I should write some value to this so that we configure. So configuring it with 00 means all the port is made as input. That's what the meaning they are actually making. So LDI R20 0x0, they loaded the value 00 and then they loaded that to the register DDRB R20. That means port B is made as input because all this DDRB register content is made 00. Now let's come to the program. So this is something initialization. Okay, this part of the code is to initialize the port B as input. That's what we are doing here. Now LDI R21 is made as 21, register is loaded with 21. Now what I'll do is I'll read it. Okay, I'm going to read this pin B. Pin B, I'm going to read. Pin B is actually the input register. So port B has pin B. Port B, it is better to tell here in this way. So port B, so this is input, sorry. So this is going to be the input and this is going to be the output. So I'm going to read this pin B to R20, which is actually port B value that comes, and I just compare R20 with R21. So in case if the port B is having 63, then there is equality condition, and if it is not equal, I'm going to keep repeating it, and if it is equal, this comes out of the loop. So that's how this is supposed to work. Now look at this another one. Write a program to find the greater of two values 27 and 54 and place it in R20. If you look at these two values are declared here, 27 and 54, and whichever value is greater, okay, that will be loaded to 20 R20 register. So these are the two registers which are loaded with the value, and you have a compare instruction. Branch BRLO. What does it mean? BRLO. BRLO is branch if lower. For unsigned I am talking about. Okay, branch if lower. So what happens if they are lower? I'm going to make it to the next. Okay, so that means I should supposed to load, because R20 is having the smaller value now. Now if it is greater, then obviously value 2 will come to the R20. That's the logic. Apart from that, you have some rotate instructions, very quite easy to understand. Rotate RD, so you can rotate with one single bit left or right. There are different way of rotation. And shift instruction, this is rotate right through carry. What we say, anything rotation will go through carry, because carry content will be moved back to MSB. That's what rotate with carry, through carry. And rotate left is again through carry. Then you have shift. See, shift is a different, rotate is different. Shift generally discards the bit which comes out of the other end. For example, if I am going to shift left, then the left side bit, this MSB is discarded, and a new bit will be added, 0, usually 0, okay, will be inserted. Here shift right, usually 0 is inserted. There is one more, arithmetic right, okay, that's again an important instruction. So where it is shifted right, but it is not inserted with 0, it is inserted with the MSB bit itself. Every time if MSB is 1, it will be keep inserting 1. If MSB is 0, it will be keep inserting 0. So it's useful for the signed addition actually. Anything with the signed number, we go for this. Apart from that, there is a swap instructions, quite easy. Any nibble wise, it will swap any number. You can see here, if your number, if your R21, let's say R21 contains 67, after the execution of this, it becomes 76. That's the meaning. Okay, so that's it about this shift and rotate. So I think some main instructions that I've covered. So further instructions I will do it in the next class.